me please make a formal introduction of our speaker, Rachel Woods Robinson. The thing that really attracted me to Rachel's field is that I noticed that she did her undergraduate work in physics. Now, I know you're probably thinking, I thought this was women chemists. What are we doing with a physicist in our midst? And the reason I did this on purpose, I did do it on purpose, is because, you see, these problems that the society is faced with these days are huge problems, okay? Very, very big problems. And we need the expertise of all of these specialties. And so I decided I'm not going to be biased against the physicist, all right? And I decided that it's very important to have a physicist's input into this problem of how do we eventually get ourselves off the fossil fuel diet, and what are going to be the things that people like Rachel are working on. So that's why. Okay, so the other thing is that in her graduate work, Rachel just didn't do like one thing. I mean, in my day, we did organic synthesis. We did organic synthesis, but what she did is she did computational chemistry. She did things where she was growing films, all right? And she was also doing device fabrication. So that this takes a lot of different skills. And so that's another reason I wanted her. And then the final reason is that I saw that she has a big interest in community outreach. And you know, the American Chemical Society, and especially the California section, does too. So I thought that would make it good. Now, for this talk, Michael is doing the recording, and Rachel has volunteered. All this is volunteer, okay? She's volunteered to be the speaker. And then the flyer that you saw was put together by another volunteer. And then I told you, you have the chance to win prizes. And that is a pretty fun part of our meeting. Okay, so what happens is that Michael and I are going to ask you 3 multiple choice questions based on Rachel's talk, okay? And I know you're worried, is Rachel going to get a prize? Rachel will get a prize, okay? All of our speakers for a given year get a prize. Yay, right? Okay, the only people who don't get a prize are people like Michael and me. Okay, so what happens is that you have to pay attention to this talk. All right, and you pay attention, and then you'll see 3 different multiple choice questions coming from Michael. And if you want to participate, what you have to do is you have to provide your answer, and you have to send it to Michael, all right, not to anybody else, because you don't want to send your answers to anybody else. You just want to send it to Michael, and Michael is going to grade those answers. And eventually, if you get everything right, you will get a ACS prize. And there's somebody here, Abigail Giamfi, has actually won 3 times, haven't you? Can you hear me, Abigail? Yeah, Abigail has won 3 times.
Thank you.
So it can be done. And by the way, she volunteers a lot. She's a graduate student at UC Merced in chemistry. computational chemistry. So she and Rachel have something in common. Okay, so Rachel, you want to go ahead?
Yes, I would love to. Let me make sure I can share my slides well. And thank you so much for the introduction. I'm really excited to be here and to meet you all. And the intention of this talk is sort of like a general overview of zooming into a solar panel and seeing what's inside. And it says host disabled participant screen sharing. I think you're gonna have to make me a co-host.
Oh, right. I have to find. I have to find Rachel. Do you see Rachel, Michael? Oh, here she is. Make co-host. Okay. Yes, I want to, so that she can give the talk. Okay.
Thank you. Okay, I think that should work now.
Yes, I think so.
I'm gonna play this and tell me if you can see my screen, like a full screen.
Yes.
Does that work? Okay, wonderful. So I'm really excited to be here today. And so I'll be giving an overview of different sort of really small things and really large things in the area of solar technology. And so basically an outline of where we'll go is we'll start at the sun. I'm going to share a video from NASA that I love. Then we're going to zoom in from the sun into the earth, all the way into the insides, innards of a solar panel down to the nanoscale, where I'll give an overview of some of the research I've done in designing new materials for solar at the nanoscale. Then we'll zoom back out and look at some big picture challenges in the area of sustainability and society for solar. And then I'll share some of my lessons from that I've learned from doing outreach, engagement, and teaching. So without further ado, I'm going to start with this video of the sun from NASA. And if you like this, there's a whole 30 minutes of this like beautiful imagery of the sun in various wavelengths. And I share this just because I think working on technology in chemistry, sometimes I get really sort of far away from the wonder of the world that is like the power of the sun that we're trying to harness here. And so I always like to come back to this video to just remind me of what we're working with and how massive it is. And so here's the Earth to scale. So the sun has enough energy to power over 1,000 Earths if we were to harness it from where we are in the solar system. This is the Earth to scale.
You are breaking out, Rachel.
I am. Can you hear me?
You sound fine to me earlier.
How about now?
It's good.
Okay. Yeah, let me know if that changes. So this is a big image, so it might start to sort of have some image issues. So let me know if that's the case. Anyways, so we're going to zoom into the Earth. And right here on the Earth right now, we have a problem. We are experiencing climate change, and we're up at the limits of a lot of our natural systems. And so I'm just going to share this plot, which is the global electricity generation share in 2011. So this is kind of when I started getting interested in science. Solar was like a tiny, tiny fraction of the global electricity, at 0.29%. So in 2016, when I started my PhD, it increased. And then a couple of years ago, now solar is almost 4% of our global electricity generation, which is amazing. It's a lot more than we were just 10 years ago. But if we want to get to net zero by 2050 to reach our climate goals, we need to do a lot better than this. And so there are projections saying that we need between 60 to 75 terawatts of solar, and approximately 16% of global electricity needs to come from solar. So how are we going to do this? One of the ways that we need to make progress is that we need better materials for solar. So there's a lot of challenges, including political, societal, economic, but materials and chemistry still is a large part of the question of how we're going to get here. So in order to illustrate that, we're going to zoom into a solar panel. So we're going to California, where most of you are. We're going into the desert, to a place called Topaz Solar Farm. And this is one of the larger solar farms in California. It consists of cadmium telluride solar panels, which is a type of panel that is, it's kind of the less common form of solar. And here is pictured 9 million solar panels. Sometimes I should have put a photo. I was flying over it the other day and I could see it from the plane. It was really fun. So if you're ever flying over the desert, look down and see if you can see these solar panels. So this is 9 million solar panels. And for scale, this is the size of Manhattan. So this is a pretty big footprint. If we zoom in more here, you can see like they're sort of arranged in grids, and here is a US football field for scale. Now we're going to zoom in to an individual set of panels, and this is called a solar array. So basically what you do is string a bunch of panels together into an array and then collect their charge and use different types of electronics like inverters, basically to get the power to connect to the grid. So zooming in further, this is a solar panel or a module. So now we're about the size of a human. So here's a human for scale doing a dance. And there's a couple different ways to wire these solar panels, but this is what it usually looks like. So inside of these panels are a bunch of crystals, but we haven't really seen where those crystals are yet and what they do. Where are the materials and chemical and physical challenges that we can work on as scientists? So we're going to zoom in even further to get a sense of that. So if you take one of these squares inside of a module, this is what's usually called a solar cell or solar panel. And you can separate the different layers into a frame, glass, and encapsulation, and a back sheet. And then there's this layer in the middle called the solar cell, which is basically what's doing the heavy lifting. And I want to note that this is just like a tiny, tiny fraction of the thickness of the panel is the actual cell, maybe 1% or less. So it's tiny. So how tiny is it? Let's zoom in even more. So I'm showing a hair for scale. We were talking about hair in our breakout room, so it's relevant. And this is about the size of a human hair compared to the thickness of a solar cell. And
Wow.
so it's pretty small. And when we get to this level, which is 10,000 times zoomed in from the human scale, you start to see what kind of looks like a sandwich. It's like a bunch of layers stacked up on top of each other. And this is a real image of a solar panel. It's a scanning electron microscopy image of the different layers inside of a solar cell. And I just think it's beautiful. It is, I've stared at this picture for hours, but I'm a nerd, but I love it. So looking at this picture, we're gonna focus on this and use it to sort of describe what's going on inside of a solar cell and how it works. So these are the crystal layers of the solar cell. And so in this case, we have what's called a back contact. So that gets charge out of the solar panel. And then this thick layer here is the absorber. So this is what sort of does the work of taking in light, absorbing it, and converting it to electricity. The stuff on top of this is sometimes they put layers to sort of act as a buffer, to just like match the electronics inside to make sure everything flows smoothly. This is also called a contact layer. And then this is the research that I work on, is a transparent top contact material. So you need light to get inside of here. So you need something that's transparent. And I'll get into this in a bit of detail in a second, but this is the general overview of the different layers in a solar cell. So let's pretend that we can step inside of a solar cell and see what happens. And this is partially from a lesson that I do with kids, so I wanted to try it out on you all as well. So please forgive the silly animations. I got really into it. So we're going to be these little electricity carrier bees today. So we're going to start buzzing around inside of this solar panel. Imagine you could move around inside the absorber. So this is an analogy for an electron. It's an electrical worker that moves electricity through the crystal. And so when the sun shines, this little squiggle is going to represent a photon, which is a particle of sunlight and basically carries a packet of electricity. So, as some of you probably know, when the photon hits the electron, it gets excited. And so we're going to represent this here with a little jiggling bumblebee. And now let's put it together into a picture of a solar panel. So the sun shines and it gets this little electrical worker real excited. And so it wants to now leave the solar panel. So it goes up through the crystal layers to this circuit. When it gets to the circuit, this is where it leaves the panel and can get turned into useful electricity like light. And so it gives its energy to the light, and now it's sad again. It doesn't have a lot of electricity, so it comes back to the absorber to start the journey again. So yep, that's my silly animation. We're going to show it for, basically, this is happening a lot, very fast, lots of electrons, and that's how we get the electricity out of a solar panel. And so you want to arrange these layers. This is a technology challenge. You want to have layers arranged to maximize the efficiency out of the cell. And I'm going to show a couple ways now how to kill a solar cell. So what happens, where can this go wrong? So one way it can go wrong is get light in, the carrier starts to go out, but then it gets stuck. So it gets stuck at the contact. And so making good contacts is a really important challenge that we're working on in the lab. That's what I do. Okay, so another thing that can happen is the light comes in, it absorbs it, but in this case, it can get stuck in the absorber. So this is not what I work on, but there's a lot of work looking into like how to make absorbers actually pass the charge and not lose the energy to heat. And then one more, just for fun, is when the light comes in and it doesn't even reach the electron. And so this is a problem that I'm also working on. We have to direct all the light into the actual absorber. It can't get stuck at the contacts. So those are 3 challenges. And now, yeah, you guessed it, we're going to keep zooming in even further. So I'm going to slice off the different layers. We're going to focus on this absorber just because there's some beautiful images of it. And so this is an image of the different crystal grains, also a microscopy image. And this is kind of like why the grains are important. So you can have really small grains and the charges move slower through that. These are larger grains called polycrystals, and you can move faster. And then in a single crystal, that's the fastest that you can move through a solar panel. So the tech challenge here is to grow high quality enough crystals so that we don't lose any energy to heat when the electricity is moving through it. Okay, let's zoom in more to a single grain. And so this is kind of like a facet. Oh, wait, I'm gonna go back. Sorry. It's about the size of a single cell bacteria. My back button doesn't work and my computer is freezing. Can you all hear me okay?
Yes.
Cool. Okay, so this is about the size of the smallest single cell bacteria. And oops. Sorry, my computer completely froze. We're gonna have to go through this whole thing again. Really exciting. That's right. So let's zoom in again. Thank you for bearing with me. And now we're going to look at the individual layers here. So these are called crystal facets. And to me, they kind of remind me of the facets of a diamond ring. And you can see here, they kind of look similar. And one of the challenges at that scale is to design facets that don't lose electricity. So if we zoom into a facet now, you can see this is a real microscope image as well. And you can start to see the actual atoms emerge at this facet interface. So this is a grain boundary where the two grains meet. And I just think this picture is beautiful. So we're bringing the bees back. Sometimes the charges can bounce along the interface and that can be bad, but other times this interface allows a pathway to travel. So it really depends on what kind of interface this is. And we can engineer that in the lab as well. So these are two things that can happen. Okay, we're about to make our final stop on our crystal zoom tour. So at this point, we're about 2 million times zoomed in from the human scale, and you can start to see individual atoms emerge. So this is that ball and stick crystal structure that most of us are probably familiar with. And this is another picture of how electricity travels. So it's moving basically between these atoms. And this is where the action happens inside of a solar cell, is like at each of these atoms. That's where things are getting absorbed. Okay, so we've made it down to this scale, and this brings us to the third section of our talk, is designing new materials for solar. So I'll talk a bit about my research here. So here, we've been focusing on this cadmium telluride material, which is a type of solar panel. Silicon is one of the more common absorbers, which the folks of you who have solar on your rooftops probably have silicon on your rooftops. There's also different types of materials like gallium arsenide. This one's called SIGs. And perovskites are an emerging field of solar. There's also a variety of different contact materials listed here. And different metal layers go into the solar panel as well. So if you put these together in aggregate, these are the main elements inside of a solar panel. And you can divide them kind of into groups now. There's some of these are earth abundant elements. Some of them are toxic and maybe we shouldn't be using a lot of. Some are really expensive, like silver. Right now we're trying to replace silver inside of solar panels. And then others are critical, meaning that they pose supply chain challenges and also abundance challenges to actually scale into the amount of solar that we need by 2050. Recently, copper has actually been added to this critical list, so I'm putting it here as well. So a challenge is to make new crystals that are made of earth abundant materials rather than critical and toxic materials. So here's a couple next generation solar materials that folks are making in the lab. I'm going to focus on this picture, which I just put this together last night. I thought it was really interesting. Like the crystals that we know about are only a tiny, tiny, tiny fraction of all the possible materials that we could make. And by material, I mean crystalline solid material. Is the space that I'm looking at in this graph. So there is a study that showed that there's about 10 to the 10 plausible, realistic stoichiometric compounds, and we only have experimentally synthesized 0.0005% of these, which is wild to me. So how do we discover new materials that could be used for applications like solar? Where do we find this stuff? So I'm gonna talk about the supercomputer and its role, and some of you are probably very familiar with this, but I'll just give a general overview of what you can do with a bunch of like computational resources that were not available even a decade ago. So one big new field is these massive databases from density functional theory calculations. So basically this is like using quantum mechanics to put together new crystals and calculate their properties. And so we can get about 10 to the 5th or 10 to the 6th compounds out of this. So this expands the amount of materials that you can look at from what I was talking about before, the experimentally synthesized ones. Another emerging field is using machine learning. It's not something I do, but it's a really big emerging field. And there have been projects that look now at millions and with the goal of having billions of different proposed crystal structures. So stay tuned for some of this stuff. There's going to be work published this year and next year with a lot of new crystals proposed. The question is, are they stable? But that's another question. So what can we do with this? We can start to be a detective, and we can take our detective lens and look at this massive set of crystals and try to search for materials that might be useful for us. So that's me with a cool hat. And I'm gonna step back a bit and show you this picture of what we call a funnel. And this is how we look through these massive data sets. So we put in a bunch, like 10 to the 5th. What was that? We put in like 10 to the 5th new materials. And then we filter these materials based on a set of properties. And then what comes out is a set of predicted material candidates that then you can do further analysis on or try to grow in the lab. So in case that's confusing to you, I made a cake in the shape of a funnel for you to look at. This was like during the pandemic, and I was really bored of my research, and I needed a real tangible representation of what I was doing. So here's the funnel cake. There's a bunch of materials that go in, and what comes out is the candidates that are useful. Sorry, I can't share the cake with you today. I ate it all in one day with some help, but it was really good. Anyways, this is the screening process. So what I did in my PhD work is I used the screening process to look for new contact materials for solar, specifically P-type, so hole conducting. It's a special kind of electrical charge. P-type contacts that are transparent to light. So I used a different set of descriptors to look through this set of materials. And this is just, I'm not going to go into depth, but these are some of the predictions from my PhD work of potential new materials that we could then try to go grow in the lab and put into solar panels. So yeah, this is about as in-depth as I'm going to go today, except I can't help myself, and I had to make more cakes in the shape of crystal structures, and I wanted to share them with you. So I made cakes in the shape of the different structures I predicted from my research. Again, this is what happened during the quarantine, and yeah, I ate a lot of cake. It was rough. But it was also a really fun way to kind of like demonstrate to my family who are not scientists, like what crystal structures were. And I think my sister finally got it. She's like, oh, you arranged them in this order. and she works in film and television. So I found that a success. So now we're going to zoom back out. And so the first step, designing new crystals, then synthesizing materials in the lab. So I then went and grew some of the crystals I predicted in the lab. Most of them didn't work, but maybe someday they will. Then we can combine layers into a solar cell to test the different materials when you put them inside of a new device. And now we're zooming back out again to a module. You can make a full-size module is the goal. And then we're going to zoom all the way back out to where we were before, which is this solar plant in the California desert, and back to the globe. Okay. So this brings us to part 4, which I'm going to talk about solar in the context of sustainability and society in general. So here's this comparison I showed at first. How do we get here to 60 to 75 terawatts? And how do we scale this in a sustainable way? So the challenge here is not only to make sure that we install enough solar to mitigate some of the severe impacts of the climate crisis, but also to do so in a way that minimizes impact during the installation from the scale up. So what I'm talking about here can be demonstrated by looking at, instead of just the tiny, like the technological part of the solar panel and the design of the solar panel, it's important that we think about the full life cycle of this technology. So I'm talking about from extraction, from mining to production. So the material processing, the refining, the fabrication of the cell and the module, and then the use phase where it's sitting in the field and operating, and we're managing it all the way to the end of life, where the panel is going to get decommissioned, sent to landfill, or recycled or remanufactured, depending on the choices that we make. So this is zooming out further than we've been before, and you can look at this. You can look at this by using life cycle assessment to assess the impacts to people and the planet across this full life cycle. And here are some of the indicators or impacts you can assess using this life cycle assessment technology. So ranging from climate change to land use to resource depletion, ecotoxicity, water depletion, etc. A lot of times for solar, folks focus on the global warming potential. So what's the CO2 emission of installing solar, as well as the resource depletion? Like, do we have enough elements to actually scale up? So I'll focus on this really quickly at the end of this talk. And so looking at extraction, these are the common elements in a solar panel, like I showed earlier. Where do they come from? They're actually distributed around the Earth in a non-uniform way. So sometimes this can become a supply chain risk when we're trying to install solar all over the world. So this isn't something I work on, but it's something to think about. It's called critical materials. And yeah, it's the goal is to have materials that are readily available throughout the world rather than concentrated in just one place. And so to look at these critical materials from another perspective, this is from the Department of Energy, just kind of showing the degree of criticality moving forward as we scale up solar. So I would recommend checking this out if you're interested. Next, we can look at production. So in solar, so this is manufacturing the panel, and in solar, as well as in most renewable energy technologies, most of the greenhouse gas emissions come from manufacture rather than mining. And so this produces a challenge which I am really interested in my current research, which is how can we reduce the energy intensity during manufacture so that our solar panels can be lower have lower embedded carbon, and how can we have a cleaner and greener production process for these solar panels. So if any of you are interested in this, I would love to talk to you about it more. So in aggregate, about 60 to 70% of emissions in solar panels come from this production phase. In comparison, maybe about 20% come from operations and management due to combustion and building operations. And this is an industrial scale solar, not necessarily on your home. So lastly, let's look at the waste, the end of life. Unfortunately, at this stage, most solar panels go to the landfill. And there have been a lot of sort of headlines saying solar is bad, it contributes to waste. And I highly recommend checking out this article that just came out a couple weeks ago, actually, where they compare the cumulative waste from solar to the cumulative waste from municipal waste and coal ash and plastic, showing that even by 2050, in the worst case scenario of scaling all the solar that we'll need to get to these carbon neutral goals, the amount of waste mass-wise from solar is just a drop in the bucket compared to other waste streams. So I thought this was a really good analysis to see this visually. So that said, we need to rapidly deploy solar, but as we do so, we can still design for recyclability and circular economy. So we still want to be able to recycle these solar panels. And the good news is that a lot of people are working on this challenge right now. And I think that we will be able to within the next decade or so. We just need to fund the research and make some companies prioritize it. So this is now putting this all together. So about 5 to 20% of emissions come from this waste, but we can also work to reduce that as we move forward. Okay, so this is compared to coal. So in aggregate, solar has more material related emissions than coal if you look at the percent of total emissions. But if you scale it based on absolute emissions, coal emits orders of magnitude more than solar, which we all are probably aware of, but I thought it was cool to look at this based on which stage of the life cycle. And then putting this all together for different energy technologies, although renewables tend to have higher material requirements, they significantly reduce the total emissions. And so this plot is really powerful. It shows basically that the use phase of these fossil fuels is, I mean, it's not surprising, but it shows graphically that that is what contributes to most of the emissions. Okay, so greenhouse gas emissions is just one impact category. We do need to focus on the others as well. And I just want to share this because I think it, you know, we make a lot of technology as scientists, but the choices that we make do have an impact. And if we're not careful, the life cycle impacts from scaling our technologies can lead to what we call green sacrifice zones. So green sacrifice zones are defined as places and populations that will be affected by sourcing, transportation, installation, and operation of new renewable technologies, as well as waste that accumulates from them. So as scientists, I believe we really need to be thinking about this as we do our research. And these are hard problems to solve, but important. So one way that people look at these kind of issues is there's a social life cycle assessment. And so solar tends to have lower social impacts than other energy tech, but we can still do better. So the final thing I want to mention on this topic is that a lot of times life cycle assessment is looked at after the technology is scaled up. And sometimes this can be too late and it can lead to something called technology lock-in. So there are disconnects between the research we do in the lab and the folks doing the analysis and then the political decision. So the analysis might design. And so I think it'd be really cool if, as chemists and material scientists and physicists, how can we apply this life cycle thinking to the early stages of materials discovery and design so we can avoid locking in technology with negative impacts? So that's my goal moving forward, is to help contribute to that process. Here's just some questions I brainstormed, like things you can look at early on when you're designing new materials, planning for the end of life, thinking about the trade-offs between energy intensity and efficiency, trying to make more energy efficient processing for solar materials. So that's the end of that section. I'm going to very briefly talk about some of my outreach, and then I'd love to chat with you guys about any questions you have. So this is a picture from one of my outreach projects called Cycle for Science. A friend of mine and I, another UCLA physics major after college, we decided that we wanted to learn a bit about science education across the country and teach lessons about climate change. So we went on a bicycle tour across the US and stopped in schools to teach science. And so we called this project Cycle for Science, where we basically combine these different elements into this silly logo. And so throughout the years, we've done a variety of different lessons. And I know some of you are teachers now, and I would love to talk to you more about some of these lessons if you're interested. But we made this 3D printed bicycle to teach about solar, and I used some of those animations I showed you earlier. Oops. We made DIY BlackBerry-based solar panels, which is a lesson that folks use sometimes to learn about solar. And then my friend did a lesson about glaciers, where they looked at modeling the flow of glaciers and discussed the climate impacts. So where have we been? So we did this cross-country trip. We also did a California-based trip in the Central Valley, and some day trips, as well as a trip through the Netherlands and one through New York. And it's been really fun. And if any of you know anyone who might be interested in joining, like, please reach out. So I'm gonna skip over this really quick, but some things that we learned: a lot of the kids that we met, they had never met a scientist before. And that was really powerful to me. I realized I was the first scientist they'd ever met. And so that came with a big responsibility. And so I was surprised how many people hadn't, and our presence was able to define what a scientist is and what we do and what we can look like. And there were also a couple of students we met who proclaimed to hate science, and then went on to play with our toys and actually have a good time. So that was really rewarding. And we wanted to show that, like, interactive science can be fun and exciting. When I was a kid, I hated science too. I was really bored by my lessons. And I think maybe showing that it doesn't have to be that way is really inspiring. Also, we learned to not mess with grizzly bears. We literally biked past a grizzly bear in the mountains, and that was terrifying. And I can share that story later. But yeah, it was very humbling. And then the second experience I want to share is that I teach a college level class called Cycle the Rockies. And this is a way to get college credit, basically for an adventure to learn about the life cycle of energy materials and learn about climate change. And I wanted to share this in case any of you know undergrads or master's students or even grad students who might be interested in this class. So a couple adventures this was this summer. We biked about 660 miles across Montana. We stopped in a coal mine, and that was a really, really interesting experience, just to meet folks who are on the ground working there. They called us the Enviros, and yeah, it was really interesting to just like see what that was like and how the coal mine interfaced with the ranching community nearby. We also went to a copper mine, and it was actually not functional yet. It was a proposed copper mine. Copper is necessary for a lot of renewable technology, and currently a lot of it comes from places that don't have a lot of mining regulations. So this mine in Montana claimed to have a lot of regulations coming up and a lot of community support. But there was still a lot of strong opposition from environmental groups and ranchers who live downstream. And so just kind of this big question, like, what's the right thing to do? We need copper. Where is it going to come from? we also stopped at a solar plant, which was interesting because we have all this cool solar technology, but installing it comes with problems. Like a lot of times there's not enough room on the grid to actually put the solar panels, and they're capped at a certain amount. So in this case, it was capped at 3 megawatts. They couldn't make the plant any bigger. It was also really interesting to see there was a lot of distrust from local communities, and the energy didn't actually go to the local communities. It went to a company that had purchased it from out of the state. So for me, someone who works in solar, like learning about some of this, the community engagement and distrust related to these plants was really important to my education. And I think it was really useful for students too, to kind of get the big picture of like, how does this science that they do in the lab contextualize with the bigger world? And yeah, zooming out to that level was really cool for me. So this is different sites that we went to. We actually went to this historic climate trial in Montana. We went to the first day, if you all have heard of it. It was Held versus Montana. And so in summary, if any of you are interested, this program called the Wild Rockies Field Institute teaches a bunch of different field courses where students can get college credit for basically going on an outdoor adventure and connecting what they learn basically from textbooks and from the lab into the bigger picture in the world. And so we taught science lessons next to a waterfall some days. We taught on a mountain. It was really immersive. We got to meet people from all over the country working on different types of sustainable practices. So yeah, let me know if you know anyone who might be interested. So in review, we started at the sun, we went to the earth, to arrays, to modules, we went to a cell, and we zoomed into this crystal layer. We went to the solar facet and all the way down to the nanoscale. I talked about different elements inside of solar panels and some of the life cycle thinking and life cycle assessment of the full process of solar panels. Some of the impacts that we can cause to the planet if we're not careful, and some of my adventures of bringing this work to the field. So my challenge to you is, what are some small actions you can take in your life that can scale up, just like we did, and build a more just and sustainable world? So that's all I got. Thank you for joining me. I'm really happy to be here and to meet you all and talk about any questions you have. That's all.
Do we
Thank you.
have questions?
I'm gonna start putting question to the audience right now, so
Oh,
at the same
right.
time we can do this.
Now you remember, you only send your answers to Michael. That's the only person you send the answers to, not to the whole group, okay? It's not mandatory. You don't have to do this if you don't want to. Everything's volunteer in the Women Chemists Committee. Bob, did you have some questions? You're about ready to put on a new solar system on your house, right? Yeah, you have to unmute yourself.
Just one question. When Rachel zoomed in down to the atom level, what technology did she use to visualize the atoms?
Wait, is this a question for the group or to me?
To you.
Okay. Okay, I wasn't sure if I was gonna ruin your contest by answering. Okay.
Oh, okay.
Has Michael put the question, because I'm not seeing anything?
It's there. It's there. You have to look for it. he was been answering them.
I can read it out loud if you want. It says Rachel's undergrad degree was in 1, chemistry, 2, chemical engineering, or 3, physics. Who was listening at the beginning? And I'll answer Robert's question now. So I was a little sneaky. I actually I showed photos from 2 different technologies, and one of them is called, like the sandwich picture was from a technology called CIGS, which is copper, indium, gallium, selenide, or sulfide. And then the crystal structure I used was called cadmium telluride. And they're very similar. They're both called thin film solar. But I was a little sneaky and combined technologies for visual effect. But thanks for asking.
I have a question. You mentioned P-type material several times. What's special about them? What is their use in the solar panel?
Yeah, thank you for asking that. I didn't want to go into too much depth just because it's kind of a very technical term. But basically, for those of you not familiar, so P-type so N-type means N means negative usually, and P-type, P means positive. So N-type means that basically the charge moving is negative, so it's mostly electrons. And P-type is this funky property where it's like the inverse of electrons are moving. So this thing called holes, it's kind of like bubbles. The bubbles are moving rather than the water is the analogy. So why it's important is because one way that the solar panel works that I didn't get into is that you have to have an N-type layer touching a P-type layer in order for the magic to happen. So there are some cases where, so there's different ways you can arrange the layers, but there's some cases where you need a P layer on top of an N layer. And we don't currently have any transparent P-type materials that are good enough for solar. None. So my research was, we were trying to find something that would work and enable a bunch of new sort of arrangements to try. That's kind of my general overview, if that makes sense. I can share more detailed stuff with you if you're curious, though.
This is Sheila. I have a question for Rachel. Can you hear me?
Yeah. Hi, Sheila.
So, hi. It was a wonderful talk, very comprehensive, really enjoyed and learned, and some didn't grasp. But the question is, in the cartoonic kind of a video display, you showed how the electrons got the energy from the sun and got stuck at the upper level at the contact. Mm-hmm. What makes it get stuck?
That's a really good question. Yeah, I also didn't go into that because it can get really technical, but so I think that was the first. Yeah, so what makes it get stuck? Okay, so when you put the different layers together, what you want is like to create sort of like a smooth pathway for the electrons to flow or the holes to flow. And you kind of want them to be able to go downstream. So imagine that they're like going down a slide. You want a slide, but sometimes if you arrange the materials in a wrong way, you kind of like create this barrier. So the electrons are flowing, they hit the barrier and they can't go over the barrier. So that's one way they can get stuck. Another way they can get stuck is that there's these like sort of, when you put two materials together, it gets really messy. Like if you were putting ketchup next to mayonnaise, they would mix and form this like aioli sauce. Okay, that's really silly. But they would like form this other layer, and sometimes that layer is not compatible with flowing charge through. It can trap the charges. And then the other thing that can happen, I didn't say this earlier, but when electrons, the N-type, when they meet holes, they recombine. So you want to keep those two, the negative and the positives, far away from each other. And sometimes what can happen is if you put two materials next to each other, they recombine. So that's called recombination. And that's one of the biggest ways that the charge is lost at the contacts, and when they recombine, heat comes out. Those are 3 ways. There's actually a lot more. It's really complicated, and I only understand some of it, but
Thank you.
yeah. Does that make sense?
Yeah, kind of. One more question about the non-science lab work or the education part. If it's only for people who are young and going to school to be part of that, you know, your while whatever the travel part, you know,
Yeah,
education. Maybe I'm not wording it properly. Like a person old like me who is kind of out of research and all that, they want to experience it and be involved in science education. Can they be part of it?
honestly, I think so. Like, you don't have to do it for college credit. You can just sign up. I know that they've had a couple people do that who aren't in school anymore, who just want to go on the adventure, so they just go for fun. So you can. I think it's not common. There's also, I mean, this is just one of many, many programs. This just happens to be one that I work with, but there are a lot of different sort of field-based programs that combine education with outdoor adventure. And I think that they have some that are designed not for people in school. But I would have to look that up. I'm curious now too. Maybe I'll look it up and get back to you.
Yeah, don't you have to be in pretty good shape to do all this bike riding that you did? I mean, I'm not sure that somebody our age could do it.
Yeah, well, here's the thing. Well, we met a lot of, it was mostly when we were biking across the US, it was mostly us, and we met a bunch of retired folks who were also biking across the US. So that was really fun. But you do have to be in a certain level of fitness. Though we met somebody who is on an e-bike.
Okay.
We met somebody who, yeah, like, and also that's the thing, it's not exactly a possible form of transportation. And so we're kind of, for a Cycle for Science, we're trying to other ways that we can do our transportation that's more inclusive. Because personally, I am not in as good shape as I was 8 years ago when we did that big trip. So and this summer, when we rode across Montana, I was like slower than most of the students. I was out of breath a lot. So yes.
I noticed on the Montana map, it looked like you guys rode on that Going to the Sun road through the.
Yes, we did.
Yeah, I just read a book on the geology of the park there, and one thing and another, and that and I have ridden it in a car, but not a bicycle. But that must have been quite an adventure.
That was incredible. Yeah, it was a little scary because there were cars too, but it was incredible. It was so hard, but it was so beautiful. And we saw a grizzly bear on top of that as well.
Oh God.
Yeah, it was a little scary. But we also got to meet with the superintendent of Glacier Park, and he was telling us that road takes up most of the funding for the national park because there's avalanches like all the time. So fixing the road is a mess. But that was the students got to meet the superintendent of the park and learn about some of the climate impacts of that are going on. And
when I went there years ago, I know they're losing the glaciers. I was there years ago. How are the glaciers doing now? Do you know?
Not great.
Yeah. I mean, yeah, with global warming, we're going to have a glacier national park with no glaciers.
Yeah, I mean, it's really tragic. It's really, I mean, I can't even begin to talk about it, but yeah, they're kind of saying visit now if you want to see the glaciers is their latest marketing, which is just really sad. Yeah.
Alex, you have a question.
I just want to say thank you very much for this talk, which covered a lot of ground and much in areas I wouldn't have expected to hear about. And I hope that you'll actually submit a couple of articles to our newsletter, The Vortex, so that the rest of our readers will get to hear about the different things you've been doing for science outreach, as well as the focus on sustainable materials for the solar cells. Because I think our readers would love to see that. And I'll just mention that I am the National Chemistry Week coordinator for the California section. And we do outreach events. We were at the Solano Stroll back in September, and we actually have 2 school events coming up next month. So I put the information about those in the chat. They're also on our website. That's where the links go. And if you happen to have some free time on November 16th, you could help us. Anyone who wants to show up at either of these schools could get in touch. And the links tell you who to get in touch with. Michael Cheng is in charge of one of the events in the evening on November 16th. That's a Thursday. And another of our volunteers, Eileen Natoli, is in charge of the morning event at Fairmont Elementary School in El Cerrito. So anyhow, if that interests you, please follow up on those links. And if you have other ideas where you want to bring something to an outreach event, it sounds like our speaker has a lot of great ideas. Perhaps she's already doing something in her local section, which would be the Sacramento section. But anyhow, I'd be happy to talk about that.
Yeah, thank you for saying that. I am also happy to share like lesson plans with, I know some of you are doing teaching and outreach too, and some of those plans are really fun and we have them written up. So if you want,
That's great.
I can send them your way.
By the way, I'm an old guy and I loved your bees.
Yes. Yes, I'm glad you did. I was told by someone they weren't professional once.
Oh, come on.
That's too much.
The bees are working, aren't they?
They're the working bees. Exactly. Exactly.
Not professional.
I know.
Jeez.
I think you reach a lot of younger people that way. It's great, make it fun, more easily accessible.
I had a question. You mentioned that you ran into kids that hated science. What were their complaints, or did they get into it at all?
Yeah, it was, I mean, this is more of like a psychological question. I think a lot of times science, okay, for me, when I was a kid, I wanted to be a musician. I did not want to be a scientist. My science classes were honestly really boring. We just read textbooks and had to memorize stuff. So I think a lot of it is maybe related to that. I think a lot of it too, what we found, and this is not like people study this kind of stuff, like what motivates people. So my answer is just anecdotal, but a lot of times, I think there just like wasn't a connection to people's lives. They're like, why is this relevant to me? No one's ever explained why this is relevant to me. So it's all it is this thing I'm forced to learn in school.
Oh, yeah.
So if that's the case, like, why would you be interested in it?
Yeah.
So I can relate. I wasn't when I was a kid. I had a really great teacher like my last year of high school, and then I had a really great teacher my first year of college, and that's why I got interested in science. But up until my junior year of high school, no interest.
Michael Gore has a hand up.
Yeah, let's let Michael, because this Michael is a new person. As far as I know, I've never heard of him.
May I speak?
Yeah.
I have a question. Thank you very much for the talk. Very good content. Regarding your DFT calculation, do you have any criteria to select this bunch of materials, and what efficiency do you think you can reach for these materials? Yeah,
this is very, I didn't get into this because it's also very technical, but I can go back to the slide if you want. No, I'll just tell you. So the different criteria. So, okay, first you want to, I use the materials project, which is like, it's I don't know if you've heard of the materials project, but that's what the group I did my PhD on runs, this massive materials database. And so first I ranked based on thermodynamic stability, basically using the energy above the convex hull. So I want to make sure that something is synthesizable. The next step was looking at either band gap or the absorption edge using absorption calculations. sorry to people who these words mean nothing to, but I'm just going to say them really quick and then we can move on. And then to like sort of assess for whether something would have sufficient transport, we looked at the effective mass, which is like a proxy for mobility. And then so we filtered down to like a smaller subset, and then we did more in-depth calculations. So looking at defects using DFT. And I can send you some of our papers if you're interested. But in terms of efficiencies, that basically the point of the transparent whole material is to have zero losses. So the efficiency would be set by the absorber, not by the material that I was looking at. But the goal is to not have the material I was looking at eat up any of the energy. So I don't know if that makes sense. But the limit is not set by what I was looking at.
Sure, thank you. When you mentioned,
Go ahead, sorry.
yeah, thank you very much. You mentioned the band gap requirements. So you have to have a match with the different layers, right?
Yeah.
Okay.
Yeah, so
Thank you.
basically you want, so imagine two on top of each other. This is what I was looking at. It has to be transparent so that the light can actually get through to the absorber. So you need the band gap to be wide enough so light can get through. Yeah.
How is efficiency determined?
So for a solar panel in general, like the basic equation is just energy out divided by energy in, which is set. There's a fundamental limit for a solar panel of about I think around 25 to 30%. It's called the Shockley quasar limit. You basically, there's a bunch of ways you can measure the efficiency when you have a device, but you look at what's called the external quantum efficiency and the internal quantum efficiency. But like you're never by stacking different solar panels on top of each other. This is what they do for solar panels in space. They put like 3 different ones on top of each other. So you can surpass that limit because you can absorb something up here, you can absorb something here, and you can absorb more down here. And so those panels have got up to maybe 50% efficiency, something like that, but those are so expensive. So they're only used in space and they're really hard to make.
I have a question about, you had a slide where it was showing where these different elements are present. And so what I want to know is, do you actually work with some of these scientists around the globe?
Okay, so the slide I was showing was like where the different elements are either mined or refined.
Right.
So I don't work on that stage necessarily, but I do, I mean, I have collaborations with people in those countries, like, but they don't work on extracting or refining.
Yeah, but you do have international collaborations. Yes. I mean, I saw that you had an international collaboration riding bikes in the Netherlands, but you probably also have a chance while you're riding the bike to talk to scientists from there, right?
Oh yeah. Yeah.
Okay, good.
I've been so lucky in my career to have been able to collaborate with people. Like I did an internship in Switzerland, and I'm a scientist in China, and I work with scientists like all over, and it's really, really cool to have that opportunity in the Netherlands too.
Yeah, no, I fully agree. I mean, you know, this was 100 years ago, but I had collaborators also in my area of research, like in Japan and in Canada and places like that. And I wouldn't have thought in my wildest dreams when I was, you know, becoming a scientist, that those people in Canada would be my colleagues, or those people in Japan would be my colleagues. I didn't. I found that to be like a big bonus.
Yeah.
Yeah.
Yeah, it's really cool to learn, like right now I'm working on the interface of life cycle assessment and materials discovery, and there's like so many different ways that people do science, and kind of putting those together has been, it's almost like they speak different languages, and I've learned a lot at like working at interfaces, and I'm sure that is a theme in other folks' career as well.
Yeah, I think that that is a very important point that you bring up, that these interfaces that you work in terms of disciplines, those people are like speaking almost a foreign language. And so you kind of have to learn that language, at least to be able to understand them, and for them to understand you, they have to learn your language. And so that's not so easy, because some languages are really hard.
Yeah. Yeah, and sometimes the same term in one field can mean something different in another field too, and that was really confusing to me for a while.
Yeah, no, I agree. That happened to me, especially when I was doing sort of interdisciplinary work. I was supposed to see. I was trained as a chemist, but I was supposed to somehow talk to mechanical engineers and chemical engineers and people like that, physicists. Okay, and I found it kind of difficult to talk to them. I thought they were speaking, some strange language.
Yeah, that was the case when I was young. Physics was taught in such a way that it was subdivided into different areas of interest, and each area of interest would have its own definition of energy.
Mm-hmm.
So there seemed to be no connection between them in those days.
They still do that to this day.
They still do that to this day.
Oh yeah. Were you trained in physics too?
I'm sorry.
Were you trained in physics?
I was thinking of studying physics at one time, but I couldn't understand the way it was taught. So at that time, I unfortunately wasn't aware that chemistry was so interesting. I find chemistry to be very interesting now, but in those days I didn't know about it, so I didn't study it in those days.
Sheila has a hand up.
Sheila.
Hi. So I did put a question in your chat directly. What I was going to say, it was interesting that social life cycle analysis will be done in addition to what the life cycle analysis for the material, energy, and the waste and all that stuff is done. Is it being done, or will it become sort of, I don't know the right word, done by the people who do, in general, the life cycle analysis in addition to the social, because many things have local impact, which hurts the local community, but the benefits are more for the other area, like what you had, the solar panel was put, but the energy was not available to the community. So who is doing that, and how will that be kind of combined? Because as an environmental scientist, life cycle analysis, I'm familiar with the social, I have thought about it, but never seen it being done kind of. So
yeah, that is like the question of the hour right now. Like, you hit the nail on the head. Is that the right phrase? Yeah, I mean, I life cycle analysis is just a model. I think it's important to say that. It's not a prediction, and it's not good at assessing local impacts usually. It's good at creating this generalized overview term. So you're right, a lot of the local impacts can be lost in this generalization. And so it should be used as like within a suite of many different sort of modeling and impact assessments. In terms of social LCA, who is doing it, I'm less familiar with sort of the methods. I think people are moving towards encompassing it in the full LCA, but social LCA doesn't necessarily mean local as well. There can also be sort of like individual experiences that are averaged and lost in a social LCA. So I think the questions, I mean, this is maybe not answering your question, but making it even more complicated. The questions that we ask matter, how we ask them, and who asks them. If it's just, I mean, I'm a scientist hiding behind a computer in a lab. If it's just people like me asking these questions about how the world works, it comes with a lot of bias. I don't have the lived experience of like what it's like to be in the mine and be out in the field. So I think we really need to partner with people who live in local communities, and not just partner with them, but have them lead these research projects, because otherwise our bias can propagate. And so who is asking the questions, who's doing the research is really important. I don't know if that's a satisfactory answer, but it should be people besides.
It is very satisfactory, and what is great is that people who are at your age, so young, thinking about globally as to who is affected, who should be heard, who should be on the table. Those are things which were not part of consideration when you were doing the ethics involved, the morality, and the effect of the broader community. So it's such a beautiful thing to know that somebody at this age group, at yours, is thinking, or there are people thinking and working on that aspect of it. So wonderful, great.
Thank you. Yeah, I mean, I think there's a lot more literacy around it, but we still could be making better choices. So yeah. Thank you for that question though. That's such a good question.
Mina.
Hi, so thank you very much for your talk. I really enjoyed the animations, very beautiful slides. It's really inspiring. So now I have a question regarding the field trips you mentioned. So I wonder if this is available through all colleges or universities, or how can be incorporated, for example, for our students, part of the program, or even field trips, like we have a part in our university who does arrange a lot of professional development as well as field trips, or even business related, that they have programs that you can learn about business related to science. I was wondering if I can introduce this program to them, but then I wonder, could it be like a one-day trip, or does it have to be a very long program? Like, is it a month of bicycle trip, or how would you think about it?
Yeah, thank you for the question. So specifically for, maybe I'll pull this slide back up again, just to have it open. What university are you?
UCI, University of California, Irvine.
Cool. Yeah. So for this program, basically, you can get accreditation basically anywhere in the US. The accreditation goes through the University of Montana. But so in the class that I taught this summer, there was only one student from University of Montana. There were students from all over different public schools. We've had folks from UC Berkeley in the past, and I don't know about UC Irvine, but we would love for you to get the word out if you can.
Sure, yeah, I'm happy to share this for sure. But then I'm wondering, how would it work for the students? Do they have to travel to a certain area and start this, or how would it work?
Yeah, so for this program specifically, basically trips are they range from about like 3 weeks to maybe 10 weeks. So it is a time commitment for this program. It's a full class. It's like a full immersive class. You can get between I think 6 units for the one that I taught, and up to 15 units for this the Colorado Plateau class on the bottom. So if you're, yeah, and it's there are other programs like this, but this one is based in Montana. So basically what happens if you're interested is like you sign up, and then you have to transport yourself to Montana where the class starts. And
I'm sorry, where in the US is that? I don't know. Is it like in the middle of US? Is it in the east or?
It is
north, right there.
North.
North. It's not. Yeah, I can't actually point, but it's
right here.
It's right next to the blue dot to the left. That's not a great description.
Oh, is she wondering about Montana? That's next to Idaho, on the border to Canada.
On the border of Canada.
It's a border town. It's a border state, I should say.
I see. Okay. So students would travel there.
Yeah. Travel there, and then depending on the class, like you take a bus or shuttle somewhere, or you start backpacking from somewhere, or basically they take care of transport from there.
I see. Okay, yeah, excellent. I'm happy to talk about our program manager about this program, and they can for sure advertise this. What was in my mind as well is that we can be also arrange like field trips, which is like in a shorter time, like take students 1 day or 2 days to somewhere. But this is a long program.
Yeah, this is a long program. I imagine there's something like available for, so I don't know if it's like, I don't know if there's something similar available for shorter trips. You could also just, like what I've done at University of Washington, where I am now, is we just arranged some day field trips. So I'm going to bring some students from UW to a solar plant nearby, not for credit or anything, just for fun. So you can just organize stuff like that. That's what I learned from doing this class. You can just call, like, to put this class together, we basically called up random people and said, hey, can we visit? And most of the time they would love to have visitors, and they'll be happy to talk to you and share their experience. So if you feel empowered to organize one yourself, or know someone who might be able to, just.
Yeah, sure. That would be great. And I'm happy to if I can have your email, and so I can introduce you to our program manager as well.
Yeah.
If you put it in the chat, yeah.
Yeah, I can put my email in the chat, and there you go. And then oh, whoops, I just sent that to one person. Sorry.
No worries.
Here we go. Yeah. So
thank you.
I do have to get going at 12:30, but I can stay on for another 5 minutes.
I don't see the email. Where is it? Oh, I see it.
Yeah, and I think Elaine can probably send it out, or whoever's doing the programming, feel free to send it out as well.
Thank you very much.
Thank you.
I will send out the email to the people who were present here, who signed up, because there are some people who didn't make it. But Rachel, we had a great turnout for a Saturday morning. People are kind of not quite in gear yet, so we had a great turnout. This is good. This is very good.
Yeah, it was really fun. I'm grateful to be able to talk to you all and learn from your experiences as well.
Yeah, but we're the main beneficiaries from your refreshing approach.
Absolutely.
I mean, in our old days, the thing was that chemistry was like not interdisciplinary. So everybody here practically, if you didn't study 4 flavors of chemistry, one of the 4, you were doing chemistry. So you had to be doing organic, physical, analytical, or inorganic, and that was it. We didn't include the people who studied biochemistry. That didn't happen until later. So
Yeah.
so the fact that you're studying and including physics and material science, that's very modern. The ACS only recognized material science basically as a bona fide subject area for the program that I coordinated called Project Seed recently. I mean, the kids can apply for a Project Seed scholarship if they studied material science, but that's very recent.
Wow.
Yeah.
Yeah.
So,
Can I
anyway.
stop the recording?
Yeah, you can stop, Michael. Thank you very